This video is proving trig identities from page 417, question 11. 11a says cos of 2x plus 1 over sine of 2x, and the right hand side was cotangent x. I started there and said, look, cotangent is just cosine over sine. Nowhere else to go, so back to the left hand side. I left the top for a while because I didn't know which version to use of cos 2x, but on the bottom, sine 2x, there's only one version. Sine 2x is 2 sine x cos x. Well, how did I proceed from here? I knew I wanted to have sine on the bottom, which means I wanted to cancel out cos. I'm supposed to end up with just sine on the bottom. So to cancel out cos, I changed this cos 2x to 2 cos squared x, hoping to be able to cancel out this cos. And so cos 2x doesn't equal just 2 cos squared, it equals 2 cos squared minus 1. And that's perfect, because then this whole piece becomes 2 cos squared minus 1, and there was a plus 1. Minus 1 plus 1 just canceled each other out, and I was left with 2 cos squared over 2 sine cos. Well, 2 and 2 cancel out, and also one of these coses, as I'd hoped, cancels out with this cos, leaving just one cos on top, and this canceled out, leaving just the sine on the bottom. And that's great, because now I've shown the left side equals right side. I have cos x over sine x both sides, therefore 11a is true. 11b was trying to prove sine over 2x divided by 1 minus cos 2x equals cotangent. Just like before, start with a cotangent. That's the same as cos over sine. And just like before, I don't know which version of the formula to use yet for cos 2x, but there's only one version of sine 2x. It's 2 sine x cos x. So I just left that, first did this one, and then realized, oh, it's going to be the same thinking as before. I want to end up with sine x on the bottom, but more importantly here, I want to end up with cos x on the top. Since I want to end up with cos x on the top, I have to cancel out this sine x. Again, I want to end up with cos x on the top, so I want to try to cancel out the sine x, so change this bottom into the sine x version of cos 2x. That's 1 minus 2 sine squared for cos 2x. Now rainbow this minus in the brackets. You get minus 1 and plus 2 sine squared x, which is great again because on the bottom, the 1 take away 1 is 0, and you're just left with 2 sine x cos x over this 2 sine squared. Again, the 2's cancel out, and like before, I have a sine x on top and sine squared on the bottom, so one of those sines cancel out, top and bottom, and on the top you're just left with cos, on the bottom you're just left with a sine. And once again, I get cos over sine on both sides. Since left side equals right side, I've proven this identity true. 11c was about proving sine x plus cos x squared equals 1 plus sine of 2x. I started on the right hand side here, and I thought, well, I'll just expand this, see what I get. I get 1 plus 2 sine x cos x. That's right from your formula sheet. Then I thought, I can expand this just by doing what we call FOIL or distributive law or expanding. And so I'll do that by saying sine x plus cos x is this squared is the same as 2 of the same bracket. This is just sine x plus cos x times sine x plus cos x. And now rainbow or FOIL, sine times sine, sine squared. Sine times cos, sine cos. Cos times sine is another sine cos, and cos times cos is cos squared. Well, that worked out well, because I know what's sine squared plus cos squared? Just 1. Again, sine squared plus cos squared, just 1. Perfect. And then sine x and another sine x, add them together, you get 2 sine x cos x, which was the right hand side. So this left hand side equals right hand side, therefore I proved it true. 11d was cos to the power of 4 minus sine to the power of 4, trying to prove that equals cos of 2 theta. I didn't know which version to use yet, so instead what I did was I broke it down difference of squares. So this is just square root each one, put the opposite signs. Cos 4 minus sine 4 is the same as cos squared minus sine squared times cos squared plus sine squared. And I know cos squared plus sine squared just equals 1. So you're just left with the left-hand side being cos squared minus sine squared, which turned out to be then easy. Which version of the formula I used? The version that has cos 2 theta is cos squared theta minus sine squared theta, because now left-hand side equals right-hand side, and I've proven it true already. Page 417, 11e wants me to prove cotangent minus tangent equals 2 cotangent 2 theta. I started with the left-hand side and did, well, cotangent is 1 over tangent. I didn't change it to sines and coses because I didn't have any sines and coses on the right-hand side. I just left them as tangents. So I have 1 over tan minus tan, and I'll do common denominator, make this also out of tan by timesing top and bottom by tan. And when you do that, you get 1 over tan minus tan squared over tan, which is 1 minus tan squared. Just combine the numerators into the common denominator. But from there, I didn't know what to do. So I think I'll leave it and do this side and think, okay, I want to get tans because that's what I had on the left-hand side. So leave the 2 out in front. Cotangent 2 theta would be the same as 1 over tangent of 2 theta. That's a rule. Cotangent is just 1 over tan. So then I did the formula for tan 2 theta, leaving the 1 on top. Tan 2 theta is just 2 tan over 1 minus tan squared, which is good because that's looking familiar. Next thing I did is I said, well, this is the same as 2 times the numerator, and then when you're dividing by a fraction, it's the same as timesing by its flip. So I timesed everything by the flip of that fraction, which puts the 1 minus tan squared on top, which is good. And then I multiplied here. I get 2 times 1 is just 2 times 1 minus tan squared over 2 tan theta, but these 2's just cancel out, and I get 1 minus tan squared theta over tan, which of course was the left-hand side. Since the left-hand side equals the right-hand side, therefore I've proven it true. That's 11E done. 11F was proving that cotangent plus tangent equals 2 cosecant 2 theta. I wasn't sure what to do on the right-hand side yet, but with the left-hand side, I knew I wanted sines and cosines because cosecant's probably going to give me 1 over sine, probably going to work with that. So I started with, okay, cotangent, that's the same as cosine over sine, and tangent, that's the same as sine over cosine. Then I did common denominators. So to get this one, I need them both to have a sine and a cos. So I multiplied this first fraction by cos over cos, and I multiplied this second fraction by sine over sine. What that ended up giving me was nice, was cos times cos is cos squared, sine times sine, sine squared, and on the bottom I just have sine times cos, and I made that into one denominator. Why was that good? Because the top is just cosine squared plus sine squared, which is just 1. So I end up with 1 over sine times cos. And that looked pretty simplified, so the question is, could I get that on the right-hand side? I hope so. I left the 2 out in front, and cosecant is the same as 1 over sine, so cosecant 2 theta is the same as 1 over sine 2 theta. Well, sine 2 theta, I'll just leave the 1 on top. Sine 2 theta is 2 sine cos. And that's nice because these 2's are going to cancel out. 2 on top, 2 on bottom, they cancel out. And you're left with 1 over sine times cos, which is the left-hand side. Again, since the left-hand side equals the right-hand side, therefore I've proven that trig identity true.